Hi and welcome to a 3DE4 tutorial. This course is all about discussing reference frames and reconstructing a set from them. In the first chapter, we learn how to shoot reference frames properly. Sounds needless, but in too many productions there are surprisingly improperly shot reference frames, making a reconstruction way more difficult than it has to be. So, we start with do's and don'ts with reference frames. In Chapter 2 and 3, we go straight to reconstructing an ancient castle shot with a drone with 3DE4's reference frame tracker. Therefore, in Chapter 2, we learn about techniques and tricks for a semi-automatic and fully automatic tracking approach. The final part explains how to create a textured 3D model in a few steps. Alright, with no further ado, let's go straight to Part 1, learning the basics of reference frames. The very first and important advice when shooting reference frames is, it is highly recommended to shoot all reference frames with the same focal length setting. That way, only a single lens object will be needed here in 3DE4, which enhances the project's simplicity tremendously. We all know, having a set of images with different focal lengths is a huge pain in the you-know-where. So, to prevent the tedious work of creating and adjusting multiple lenses in 3DE4, do not touch the lens object of the camera once it was set. The next advice, directly related to focal length, is do not modify focus within a set of reference frames. Make sure all pictures were shot with the same focus setting. Why so? Glad you asked. Let me quickly explain the influence of focus with the help of these three images. Here we have a nice painting located in front of a green screen. All of them were taken with different focus values. The camera itself was locked. It did not move in any of the three pictures, nor was focal length changed. Nevertheless, when we scrub through them, we quickly see we basically zoom into the set. Zoomed into the image, we see even a very slight focus adjustment has a noticeable effect on the image. But wait, zooming? This can only mean modifying focus results in a modification of focal length. And as mentioned, this is bad since it would lead to multiple lens objects in 3DE4 as well. We clearly don't want that. So make sure, once focus was set, the little switch at the lens is set to manual focus and the lens isn't touched afterwards. To understand why focus changes has a direct impact on focal length, let's have a look inside a camera lens. A lens is an optical device consisting of multiple elements that both diverge and converge light to focus it on the image sensor. The reason behind this diverging and converging is that the image sensor is usually much smaller than the view we are trying to capture. Therefore, it is needed to bend the light to reduce the size of the image. If all rays are collimated, the so-called point of convergence, our image is focused. Without going too much into detail, there are excellent websites explaining this topic. We can state that to change focus, the elements inside the lens are moved to bend the light rays differently. Light rays will hit the image sensor differently. The point of convergence is modified, resulting in a physically different distance of this point to the image sensor. The exact same thing that happens when changing focal length. The result can be seen clearly by these images. There's an actual zooming. So, bottom line, once set, never modify focus within the reference frame sequence. Period. Okay, next one is camera settings. A camera today provides several automatic, semi-automatic and manual modes. One mode in particular is very convenient for shooting reference frames. Let's think a moment about what kind of image we'd like to shoot to get great reference frames. Clear and sharp images with as little depth of field as possible. For this purpose, mode AV or A on some cameras helps best. AV or A lets us define the aperture and sets shutter speed accordingly. Why a fixed aperture is quite important is shown with the help of these images. Again, it's the nice painting. All these images are shot with different aperture values to demonstrate its effect on the image. Of course, focus was fixed, as the camera itself. When scrubbing through all these images, we quickly see the background becomes more blurry with each picture. Why does this happen? Simply put, the aperture regulates how much light is allowed through the lens by varying the size of the hole the light comes through. This hole with its mechanism is the so-called aperture, and its size is displayed by the f-stop number. With a low f-stop number, the hole is wide open. Therefore, uncollimated rays gets to the image plane, resulting in a sharp focus only for rays coming from a certain distance. In such cases, the image is only sharp at the focus point, while all parts before and behind are blurry. With a high f-stop number, the hole is very small, resulting in highly collimated rays. This results, you might guess it, in an entirely sharp image. Well, how does this affect reference frames? As we learned, for great images, focus has to be fixed. Therefore, we are quite unflexible considering the focus point, more precisely, the focus range. If big areas of the image are blurred due to a widely open aperture, and therefore a small f-stop number, like 1.8 here, it's a lot harder, if not near to impossible, to precisely track features within these areas. So, it's quite an advantage having as much of the image as possible in focus range and therefore sharp. A small aperture, on the other hand, like an f-stop of 22 here, gives us a big focus range, providing the possibility to track features everywhere within the image. So, remember, a high f-stop number means a small aperture and therefore a sharp image. Great, we're moving forward. Next advice is ISO settings. Again, we prepared another project for demonstrating ISO effects. A wide range from ISO 100 to 6400 was used. As seen by the camera names, there are 5 shots for each ISO setting. Okay, let's have a look at these sets. When scrubbing through each ISO value, we notice the images are getting grainier and therefore image quality more and more a catastrophe. Why is that important? Grain modifies the image information from one image to another. When having a closer look, the influence of grain can be seen very clearly. It may be not much for our eyes, but it has a real impact on analyzing an image by the automatic tracking engine. With ISO 100, there's just very little grain in the image and therefore the 5 images of these set do not change drastically. So, no problem at all for 3DE4's tracking engine. But with ISO 6400, please note this will be hard to look at, viewers' discretion is really advised. It's all trash. Even for our eyes, it will be hard to precisely track the wooden edge, for example. Obviously, such images won't really help the automatic tracking engine. It will be much easier getting good tracking results if image information does not change as much as they do with all that grain. But how does this happen? ISO determines how sensitive the image sensor is to light. What may be a helpful feature for shots at night is quite unhelpful shooting a scene with sufficient light. In most scenarios, a slow shutter speed compensates even low light situations, so there's hardly a need for increasing ISO. And this leads us to the last advice of this part. Use a tripod. As we could see, to get a clean and sharp image, it may be necessary to shoot with long exposure times. It's highly doubtful to achieve this with your hands alone. Okay, to sum it up, use a tripod, keep the same focus settings in all reference frames, set aperture to the highest value your camera provides, and last, set ISO to 100. Following these few and simple rules will help a lot during tracking later in 3DE4. This chapter is all about reconstructing a building seen in a set of perfectly shot reference frames. Of course, shot with all the tips we learned previously. Importing reference frames in 3DE4 can be done the easy or hard way. Unlike a typical sequence, we will need an individual camera object for each reference frame. So, in folder Set Reconstruction within Tutorials 4, we see 17 images. Oh boy! Better use a more comfortable way than importing each frame individually. Select Script 3D4, File, Import multiple reference frames. In the upcoming requester, simply set the folder containing all reference frames. Parameter file pattern can be left untouched, since all images within this folder should be imported. Great, there are a bunch of new cameras in Object Browser, each one containing a different image. Okay, so delete the redundant sequence camera and have a look at the images. A quick tip, all images aren't buffered so far. Instead of manually selecting all frames, there's another nice script which can help us doing this. Select Playback, import reference camera footage. Alright, while 3D4 is going through all cameras, have a look at the footage. We see a beautiful ruin of an ancient castle, maybe enchanted, within a wood and beside a river. This castle was shot with a drone from different heights. As mentioned, this chapter is all about reconstructing this castle. For this purpose, we will practice two different approaches to create tracking points: a semi-automatic and fully automatic tracking. At first, the semi-automatic approach is shown to discuss some fundamentals of tracking points in a reference frame project. And we begin with the most fundamental question of this chapter. How do we use reference frame tracking? So easy, it's the same as manual tracking. Simply control-click on a feature, and here we go. A tracking point was created in the current camera. Of course, it behaves identically to a tracking point within the sequence. Just the outer search box used in sequence tracking is obsolete here, since the defined pattern will be searched within the entire image. To track this feature, click on button Track. The reference frame tracker starts to search the defined pattern in other cameras, in the order set in Object Browser. Since all cameras are represented as one frame in Frame Slider, we refer them as frames throughout this course. Okay, there are a bunch of tracked frames. Let's have a closer look at tracking quality. Awesome. The tracking is amazingly precise. Using this precise tracker, we can track so many more features instead of just those only identifiable in every frame by our eyes. Alright, having this opportunity, let's use this moment to discuss some do's and don'ts at tracking in a reference frame project. Let's have a look at good and bad features for tracking. This wall looks good, as proven just a second ago. Also this one. Basically, every wall providing a flat structure is suitable. But unlike some users think, an edge is not. Why so? Simply, it is a 3D structure changing its appearance when looking from different point of views. More specifically, there isn't just a 2D transformation like on a flat surface. The depth information and overall structure of this edge is entirely different here compared to the previous frame. It derivates too much from the original set pattern in other cameras, so it cannot be found. By the way, regardless what's set in tracking mode, 3DE4 will always use the pattern tracker to track a feature in a reference frame project. Let's demo this and choose some edge. Maybe this one between tower and wall. Right after tracking started, the reference frame tracker isn't able to find the edge in other frames. Compared to sequence tracker, the reference frame tracker is much fussier. In case of tracking errors, instead of moving away from the original set feature, it won't set any point and skips the respective frame. However, if we move this point a bit to the right wall so the edge is outside the pattern box, and then restart tracking, nice, we're back on track. The feature can be tracked in more frames. Another example of how 3D structures interfere tracking can be seen on this wall. This wall seems to be flat at first sight, but right after tracking started, again, not good. With a closer look at the wall, we see why. there's a leaping brick in the area of this wall, which wasn't obvious looking frontally on it. Again, this brick changes the depth information and therefore the structure of the wall. To sum it up, it is highly recommended to use features on flat surfaces. Alright, enough theory. Let's start tracking some features. As we know from sequence cameras, we need a minimum amount of 6 tracking points to calculate the project, without any survey. When tracking points in reference frames, it is recommended to have at least 8 active points per frame for a good reconstruction. In Timeline Editor, 3DE4 can display which frames don't have the necessary amount of points with red bars. To change its default amount, set option Timeline Editor, show red frame markings to less than 8 points. Great. Now everything's set and we start with a nice feature on the flat wall. Like this one on the tower in the back. This side of the tower can be seen in all cameras, so it should be quite easy to find features which can be tracked in all of them. Create a new point, adjust its size, then click Track. Nice, the reference frame tracker really finds this pattern in nearly every frame. Have a quick look at tracking quality. Really nice. As in the previous demos, tracking quality is amazing. So, most of the frames could be tracked, but as we can see, there are a few left. To fill these gaps, have a closer look at these frames in Frame Slider. Unlike tracking points in a sequence, a tracking point in a reference frame project does not have the states of tracked and splined. Since all frames in the timeline are individual cameras, the tracking point is in fact a keyframe in every frame. So, we also know from sequence tracking that a keyframe can be used as a new reference for further tracking. This technique can be adapted here to fill these gaps. Simply select a tracked frame, preferable one with a quite similar point of view, then click Track. The pattern in this selected frame is now searched in the remaining frames. And as we can see, quite successfully. Just one frame left, so choose another keyframe, then track. Great, point 1 is complete, and as expected, with an incredible tracking quality. Point 2 is already waiting, again search a feature in a frame. As we learned, since all frames are individual cameras and therefore a point is a keyframe in all of them, we are free to start with any frame and are not bound to frame 1. So maybe choose frame 8, for example, and a feature on this wall. Create a point. Good. Again, always make sure the set pattern is on a flat surface and does not contain any edges, for example. Great. Then track. Well, we see this point wasn't tracked in as many frames as the previous one. At first, check the tracked frames. Looks great. Next, have a look at those frames in which nothing could be tracked. We notice that some frames are impossible to track since the defined pattern simply isn't visible in them, or they are distorted too much for a perspective adaptation of the original pattern. So these frames better should be excluded to prevent 3DE4 wasting time due to searching the pattern in these frames. Otherwise, it's just really inefficient. To exclude them from being tracked, we can use the frame range. Use the white handles to set a new tracking frame range. Looking at the footage, we can leave out frames 4 to 6. Alright, select a keyframe as a new reference. By the way, it is possible to use a keyframe outside the frame range. Let's do this. Then click Track. Looks better. Still a few frames left. A quick look at them. Here we see those 2 frames cannot be used for tracking as well since the feature isn't really visible in them. So basically there's just 1 frame left. Again, set the frame range accordingly. Choose a different frame, then track. No success. Maybe another different frame? What a bummer. Seems we won't get a result with the reference pattern technique. But of course, 3D4 provides a different one to solve such problems. If the current point could already be tracked in a bunch of frames, it's showtime for script align to key, found in display area and menu tracking. Script align to key, as described in its more info box, aligns the currently selected point to the previous or next keyframe, depending on tracking direction. To use the script, a point has to be placed manually on the feature. The script then fine-tunes the point position based on the previous or next keyframe. As we learned, when tracking reference frames, there is no tracking direction, so it will always use a keyframe before the current frame, and in case there is none in the active frame range, it uses the one after. The manual placement doesn't have to be precise, rough is sufficient. Activate Align to Key, and boom, the 2D tracking position is adjusted. By the way, to be on the safe side, if this keyframe will be used as a new reference, either by the tracker or Align to Key, change the pattern box to exclude this edge. Perfect. We have a second point that could be tracked in every frame the feature is visible. Okay, on to point 3. Maybe this time we choose a feature on the ground. Like this one within the castle. Looks pretty flat, so create a point. Adjust its size. Then track. Well, not as expected. At first, again exclude all frames which do not or hardly show the pattern. At features like this one, the reference frame tracker needs a little more, let's say, motivation to find the pattern. This extra motivation can be controlled by parameter deep tracking. As the name indicates, a higher value forces the tracker to search deeper for the defined pattern. Let's increase it a bit. Of course, this decreases performance, but at the end we get a tracked point that couldn't be tracked otherwise. Again, hit button, track. Hooray! There are some more frames, but still not satisfying. Patterns on the ground are always harder to track than points on vertical structures due to their bigger 2D transformations. In addition, we can see in the other cameras, this stone structure isn't really flat, but at least almost, unlike the leaping brick we've seen previously. The solution is to reduce the box size to exclude as much uneven structure as possible, and an even higher deep tracking value. Let's set a higher deep tracking value and see if there's room for more improvement. Now we notice the slower performance, but more tracked frames. Much more than previously. Let's continue tracking until all red bars are gone, with the techniques we recently learned. Frame ranges, using existing keyframes as a new reference, Align to Key, and deep tracking. Good. As indicated in Timeline Editor, there are enough points in every frame to calculate the project. There are tracking points on each side of the castle. Very good. So, calc the project. Well, deviation clearly shows a problem with our project. What happened? Tracking errors can be excluded from a potential issue list. When checking a tracking point more closely, its high tracking precision can be seen. It seems the lens must cause the high deviation since it's still set to default. We have to adjust its parameters to the footage. Okay, the best preparation for a reference frame project like this one would have been a previous camera calibration with lens grids. But we were lazy and, well, for the purpose of this demo, it is sufficient to adjust the lens here. By the way, there is only a single lens object for all cameras since all footage were shot with the same lens and, important, also shot with fixed focus. As we learned in Chapter 1, focus changes are very bad for reference frames since, you remember? Right, they cause focal length modifications. Open Parameter Adjustment and adjust parameters focal length and distortion degree 2. The footage does not show any massive lens distortion, so these two parameters should be sufficient for a good reconstruction. After a while, adjustment has finished. So, transfer parameters. Then again, calc all. Wow, deviation was reduced by a factor 100. Incredible. Finally, a quick look at the reconstructed scene in 3D orientation controls. Beside the reconstructed 3D points, we clearly see all reconstructed cameras in their positions in 3D space. As seen in footage, we have 3 rows. Okay, the reconstruction seems great. Just 3 quick modifications are needed to perfect it: distance constraints, scene alignment, and baking. At first, distance constraint. Since we try to reconstruct a real-life castle, it would be quite convenient to have its real-world scale here as well. Luckily, someone measured a distance on the set. More precisely, the width of this platform. These 2 points were tracked as closely as possible in the corners of the platform, so they are great for using the distance value. Back in 3D orientation, select Constraints, create distance constraint. In the upcoming requester, enter value 278 centimeters. Alright, the whole scene is now compatible with the real-world scale. But we notice the grid is now way too small for the new scene size. So increase it to have a good reference for aligning the scene. In the project attributes, set grid size to 100 centimeters. Oh great, the result is a camera jungle. Object sizes in 3D space are locked to the grid size, so better we scale down the camera objects so we again see points and grid. And better turn off the image plane as well. Much better. So go on to alignment. It seems, by looking at the cameras and 3D points, the scene is already almost aligned correctly, but it won't hurt to improve it a bit. Select 3 points on a flat surface, like this wall. Then, select Edit, align 3 points to YZ plane. Next, select a point near to the ground and move it to the scene's origin. That's it. The last step is baking the scene to create real survey out of the reconstructed data. Select Edit, Bake Scene. Et voila! All points were converted to exactly surveyed points. Calc all again, and we're done. If you like, feel free to restore the original scale of the camera objects, which is now messed up due to the baking. Perfect. With some simple steps and techniques, we could reconstruct the cameras and some points. This was the semi-automatic approach to tracking features in a reference frames project. 3DE4 provides an additional approach, the fully automatic reference frame tracker, improving the chill factor in your coffee breaks tremendously. Okay, start from scratch. Let's create a new project to get rid of all the points and results of the semi-automatic tracking. Good. So, how does fully automatic tracking works with reference frames? Well, it's the same and as easy as the usual automatic tracker. First of all, switch to Auto Tracking Controls. Display area changed. But before we click on Auto to continue to Auto Tracking settings, have a look at the footage, especially at its contents. The job of this course is a reconstruction of this beautiful ruin of an ancient castle. As we can see, there are a lot of things going on before, beside and behind the castle. There's grass, rail track, a river, and a wood providing many features the auto tracker would love to track. But we don't. Any features tracked within any of these areas are completely unhelpful for reconstructing the castle, and therefore drastically decreases performance. So, the answer of this problem are masks to exclude all these areas. Add a new mask to this camera. With default settings, this mask is designed to exclude anything within its shape. Here, instead, we'd like to define an area enabled for tracking and exclude everything outside the shape. So, in Attribute Editor, invert the mask. Good. Now modify and add CVs to adjust this mask to the outlines of the castle. But before, change the interpolation of existing CVs to linear. This castle naturally has only sharp and linear edges instead of being an organic structure. Therefore, we need only linear interpolated CVs. If now a new CV is added to the mask, its interpolation will be set accordingly to the neighboring CVs, so it's linear in this case. As we learned in the previous chapter, tracking edges increases the possibility of tracking points only in a single or few frames. So, it is recommended to exclude all these outer edges of the castle as well. Nice. We have a mask covering the castle. Well, of course, this was just the first frame. There are 16 left and, yes, since there are loose reference frames, we have to adjust this mask in every frame individually. In addition, each camera in 3DE4 contains its own mask, so basically we need, 17 different masks in total. But before starting like a maniac and create new masks in every frame, 3DE4 provides a tool to help us here. We do have a mask that would suit quite good in this frame, so let's use it here as well. Duplicate Mask duplicates the selected mask from the previous frame, with all its set CVs. Now we have the basic shape of the castle for a much easier adjustment to this point of view and don't have to start from scratch. Okay, we have masks in every frame. Everything's prepared, so select button Auto. In the upcoming window, we see several options to control the automatic tracking. Most of these settings may be familiar from auto tracker parameters used for sequence tracking. Anyway, let's have a look at them since some behave differently. Points per frame sets the targeted amount of points per frame. Min track length defines that a point can be kept if it could be tracked at least 3 frames. And as max length, we should set approximately 13 frames for the sake of performance. There are just a total of 17 and as we know, with very different point of views hiding some sides of the castle in some frames. With a lower value, the auto tracker isn't forced to search the feature longer than necessary. Okay, pattern size should be quite small to prevent any edges or windows within the pattern. Minimum distance will be a bit higher than the default value. All points should be best placed equally on the entire castle. Parameter action defines which passes should be used. This will be explained later during tracking. Deep tracking has the same effect as shown previously. For best performance, we leave it to 0. Max passes per point will be important in pass 2, so again, we'll get later to it, but 5 is an appropriate value. Before starting the tracking procedure, open again Timeline Editor to display better how the reference frame auto tracker works. As previously, with the semi-automatic approach, set the indicator to less than 8 points. Great, There's nothing left to do, so select button Track. 3D4 instantly could find some patterns in the first frame, then tries to track them in all the other cameras. The procedure is pretty much identical to the previous semi-automatic approach. The first pass is finished, and the second pass begins right away. In this pass, the auto tracker uses the same technique we applied previously to fill the gaps. Already tracked frames will be used as a new reference to try tracking the remaining untracked frames. How many times this second pass will be applied was set with parameter max passes per point. In our case, 5 times per point. After that, again pass 1 starts with finding new features in a different frame. Time for a nice coffee. After a while, our nice little tracking servant could track enough points in every frame. All red areas are gone. The fully automatic tracking procedure has finished, so let's have a closer look at the track points. Great, there are some points widely placed across the image. Time to calc the project. Well, deviation isn't very good. What is wrong? The lens is already adjusted, so the problem should lie somewhere else. Like in sequence tracking, there might be some falsely tracked points interfering with the reconstructing result. As we can see in Deviation Browser, there are some really messed up points. Now, simply deleting points purely based on their deviation is not entirely wrong and would improve the reconstruction quality. But points with such a huge deviation might influence other points, and by simply deleting the highest deviations, we might accidentally delete actually good track points. So there might be a better and more reliable way. Also, like in sequence tracking, there's a nice feature helping to detect such points. Simply open Calc, find badly tracked points. In the upcoming requester, we can set which points should be evaluated. For this course, we leave it to automatically track points only. All found points should be only selected, and sensitivity can be left untouched as well. We start with the default value, and in case the algorithm doesn't find enough points, start another procedure with a high value. Okay, start the procedure. The complex algorithm behind find badly tracked points does not simply look for deviation values, but, to explain it very simplified, checks the triangulation of each point towards each other. Nice, some bad points could be found, so let's get rid of them. Of course, this method isn't the holy grail of removing bad points, but it's a great help. Calc all again. Seems we won't need another run with a higher sensitivity value. To check this result, use 3D orientation controls. And here we go, it's pretty similar to the previous semi-automatic approach. Okay, there's now a reconstructed scene with cameras and 3D points, but for a good reconstruction of the castle, still too few ones. Of course, we could have started with more active points per frames in the first place, but as always, that would have cost us a lot of performance. A different approach is simply using the now existing 3D camera data to track more points much quicker than before. By using 3D data for tracking, the reference frame auto tracker is able to reduce the area used for finding set patterns in other cameras, which is way much faster than without this information. So let's do this. In auto tracking, click again, auto. And activate toggle button, use 3D camera data. Further, increase the number of active points per frame. All existing points are considered as well for this amount, so if there are already 10 points, there won't be tracked anything additionally. Last, Since the 3D data promises a higher hit ratio for new tracking points, we can set action to pass one alone for a much lower tracking time. Alright, start the tracking. This technique is also highly suitable for camera data from this semi-automatic approach. Simply track some points with this approach, adjust the lens, calc all, and then start a fully automatic tracking. Combining the two approaches this way is the most efficient and fastest way to create tracking points in a reference frame project. But for the sake of the length of this course, in this video we stayed in this project and used its data. Great, we have a lot of additional points, so calc all. As we see again, we should sort out some badly tracked points. Leave it to default parameters, except this time 3DE4 can delete every found point immediately. In 3DE4 we trust, right? Alright, some points could be removed from the project. So calc all. Much better. Although we have an adjusted lens, this adjustment is based on completely different points. So fine-tune the adjustment for this project. Add focal length and distortion degree 2. Then adjust. Right after transferring the parameters, calc all. Switch directly to 3D orientation controls. Like in the previous chapter, the next step would be setting the distance constraint and align the scene. But we skip that in this step and go straight ahead to the next chapter. This chapter demonstrates how to use the reconstructed point data to build a textured 3D model of the castle for exporting it as an OBJ. For this purpose, we use a 3DEqualizer merge file containing several manually tracked points across the entire castle. This project is downloadable at 3DEqualizer.com in section Downloads Tutorial Data. As we can see, there are enough points available. As done in chapter Semi-Automatic Tracking Approach, the reconstructed point cloud has real-world scale due to the distance constraint and was aligned to the global coordinate system. Further, the great deviation indicates that there are well-adjusted and reconstructed cameras, which is a very important foundation for creating a textured model of the castle. So, everything's prepared, let's start with creating a mesh. The task here, as set by our supervisor, is to reconstruct the tower and wall in the front, the side, as well as the white tower in the back. When looking at the footage, it becomes clear that unfortunately not every side can be seen here. There are parts of the castle which are impossible to track and reconstruct since there's no footage of them. But of course, we can reconstruct all visible parts. Therefore, we split the castle into 3 reconstruction steps and later combine all of them. Another advantage of this procedure is efficiency. The different parts have different characteristics regarding the amount of details, for example. Having the opportunity to apply individual settings helps tremendously, but we'll see this in detail within the next steps. Okay, so start with the left tower and wall. As seen in the footage, the leaping wall in the middle is one of the things impossible to reconstruct entirely, since its left side isn't visible in any cameras. So, this wall defines a natural border for the first reconstruction part. In 3D orientation controls, it might be hard to precisely select the 3D points belonging to the tower and wall. Back in manual tracking, it's way easier. Simply select all tracking points placed on the object. Great! In 3D space we can have a last check if points were overseen, but it doesn't look so. Create a mesh out of the selected 3D points. Open menu 3D Models, then click Create, Mesh from Points, Legacy. Advanced scanning is more suitable for more complex structures with a lot of points, but with the downside of being a bit slower. Therefore, Legacy is perfect for our purpose here, with its high speed and the relatively simple structure of the castle. The procedure shouldn't smooth anything. The mesh should exactly follow the point cloud structure, so set parameter point filter to 0. Alright, we have a mesh. But as we immediately notice, this doesn't really look like a round tower with a wall. Having a look at it in lineup, we see the mesh covers the area including the ground in front of it. Its basic shape and position is great, a great foundation for the next step of refining the mesh, so it becomes a 3D model depicting a round tower and wall instead of just a flat surface. But at first, a quick cleanup is needed. This polygon doesn't belong to tower and wall at all, so it will lead to false reconstruction results and drastically decrease performance. Back in 3D orientation, activate toggle button, remove poly. Then click on the targeted polygon and its lines. By the way, here we can see quite good how much control we have with manually placed tracking points about what should be included in the 3D model and what not. For example, if the task is just to reconstruct the lower part of tower and wall, simply create a mesh without the points of the upper part. It's simply highly efficient. Alright, a last check in 3D orientation. Oh, there's a very narrow polygon, even overlapping other ones. Better remove it as well. A quick additional tip before we continue. So many cameras in 3D space can be quite annoying, so if you like to hide them, select View, Show Cameras, Current Camera Only. Much better. Good. Have a look at Texture Projection of the current mesh. Select the 3D model, then set parameter Texture Mapping to Project Footage on Polygons. For a better view at the texture, hide its lines. Okay, we quickly see it's far away from being sticky on the 3D model. Of course, there are some cameras showing a distorted texture, since these cameras are positioned lateral to this side of the castle. But overall, it is obvious this 3D model is not a good reconstruction. So, time for refinement. 3DE4's refine procedure will subdivide the existing 3D model and optimize the added vertices 3D position based on 3D camera data and footage. More details are added to the base 3D model for a far more accurate reconstruction of real-world tower and wall. Open menu 3D Models, Refine Polygons. In the upcoming requester, have a look at the parameters. Resulting geometry defines if the refined model should override the existing one or if a new one should be created. In most cases, create new 3D model is recommended to keep the base model for having the possibility of refinements with different parameters. Average triangle edge length sets the initial polygon size. A high value results in big polygons and a low one in small ones, influencing the quality and speed of the refinement. This value is defined in length units, so what's the ideal one for our mesh? The grid in 3D space helps us here. As we see, one square of the grid is 100 centimeters, so having a closer look at the size of grid squares and 3D model, 100 centimeters might be a good value to start with. Finding the ideal edge length value is definitely a bit of trial and error, but the relation of grid size and model size is a great indicator. Okay, back to refined polygons. Then set this parameter to 100 centimeters. Next, use footage sets which camera and therefore which footage should be used for refinement. Here, we just have footage of the castle in all of them, so use all reference cameras. Toggle button Use Auto Tracking Masks defines Well, as the name indicates, if auto tracking masks should be considered. In most cases, this won't be needed. Adaptive triangle subdivide gives the procedure the opportunity to subdivide triangles even further for more detail at specific parts. The higher the value, the more possibilities the refinement has, but as always at cost of performance. So here again, that's a parameter for trial and error to find the ideal value. Okay, sensitivity to image details value depends on camera quality. If we have badly reconstructed and adjusted cameras or very uneven structures, a lower value will decrease the refinement sensitivity to image details for a higher chance of getting a refined mesh. With a high value, more details will be considered, resulting in a more detailed 3D model. But for this, precisely reconstructed and adjusted cameras are inevitable. In most cases, this parameter can be left to 0.5. Last, quality is a parameter for cases with few cameras or complicated footage content. A higher value forces the procedure to work longer on footage in such cases, but of course drastically decreases performance. This parameter might be a great help if the mesh cannot be refined properly otherwise. Alright, everything is set, so click button Refine 3D Model. We instantly see the original mesh was subdivided according to the set edge length parameter. The refinement process in this video was sped up to demonstrate better how the refinement works. Typically, such a refinement needs around 2 to 3 minutes. This high speed gives us the opportunity to try different parameters for an ideal result. Okay, while I was speaking, we saw how the 3D positions of the added vertices are optimized, leading to a good reconstruction of real-world tower and wall. After it's finished, we see the new and old 3D model, with the old one still selected. In Object Browser, within the current point group, both are listed. Let's hide the old model and have a look at the new one. Amazing! In such a short time we got a 3D model which really follows the tower's curvature and some details of the wall. Stunning. In approximately just 2 minutes, the refinement procedure added nearly 500 points and 900 polygons for this object. Considering the details, such a low poly count is great. When scrubbing through all cameras, we quickly see the improvements. There are far more surfaces being sticky to the mesh, indicating a good reconstruction. But having a closer look, we see that parts of the 3D model, like this edge, this window, or also the grass ground, are not yet satisfiable. It seems the current triangle size is too big for these details, so let's try another refinement. Hide this model, then show the original one. By the way, great we still have it, right? Then back in Refined Polygons, we have two options. First, set a lower edge length value for smaller polygons, but this will lower the triangle size globally, and we saw just specific parts of the 3D models need them. Most of the 3D model looked already great. Time for Adaptive Triangle Subdivide. As mentioned, this parameter gives the procedure the freedom to adaptively subdivide the 3D model further if needed. That improves details in the model without drastically increasing refinement time. Set parameter to, well, approximately 0.4. Then start again. Like in the last refinement, the 3D model was subdivided and optimized. But this time we see that the procedure adds even more polygons at edge, windows and ground. Exactly what we wanted. Okay, hide the original mesh and have a look at the new one. This model looks a bit better than before, especially the edge is a bit more precise. All with just roughly an additional 100 points in polygons. Feel free to play with the parameters for an even better refinement. For this video, we consider the first part of the castle to be reconstructed. So go on to the next one. The walls in the front and at the side. Again, use manual tracking controls to select its tracking points. Check the other side in other cameras. and add them as well. By the way, every surface of the real-world object that should be included in the base 3D model should have at least one tracking point. Back in 3D orientation, check them. Oh, there's one missing. Okay, all points covering the area for reconstructing are selected. So create a 3D model. Again, with no point filter. Having a look at the model, we quickly see there are also polygons not belonging to the wall. So remove them. A quick check in lineup. This one at the side should be removed as well. Good. Seems we have a nice base model for refining. In the beginning of this chapter, it was mentioned that this castle reconstruction is split into several parts due to the lack of footage for some sides of the wall and for the opportunity to refine parts with individual settings optimized for their specific structures. This method results in a high efficiency, so let's do so. When having a look at this part in the footage, we quickly see there are far more details than previously. More edges, more ground. The overall structure is far more complex than in the first part. It is obvious that the last setting won't lead to a great result. So, back in Refine Polygons. At first, average triangle edge length gets a lower value. Maybe 75 centimeters since the overall structure is more detailed. Next, adaptive triangle subdivide can be increased even further. Sensitivity and quality can be left untouched, since we have good cameras but relatively complex content. So, we try this setting in the first place. Start the refinement. By the way, as soon as the procedure starts, texture mapping is automatically set to project footage on polygons. Okay, the procedure is finished. Have a look at the 3D model. Great, these settings turn to be out sufficient. This detailed wall appears to be refined quite precisely. However, like at the first model, the footage projection is really distorted due to the current camera's point of view. This will be solved later with texture mapping. Again, considering this complex structure, a poly count of approximately 3600 is fantastic. Good. The last part, the white tower and ground before it, are already waiting. Same procedure as the last two times. Select all points, create a raw mesh, clean up, then refine it with settings suiting for this part. Have a look at the third 3D model. Well, it seems there are some problems. If we look closer, the ground merges with the wall in a quite strange way. That's definitely not a hard edge, as seen in footage. There are several factors that may cause this wrong refinement. Badly tracked points, badly adjusted lens and therefore insufficiently reconstructed cameras, or image quality. The first items can be dismissed. The former two 3D models prove that we have quite precise cameras. So, have a look at footage. When we zoom into the picture, we see it gets blurry and pixelated. Unlike the wall in front of the castle, this white tower and ground are very far away from the camera. Therefore, the actual amount of pixels available for this area are quite small, which in turn has a much bigger influence than a refinement of an object close to the camera. Let's have a look if we can handle this with a different setting in Refine Polygons. Edge length can be kept at 100 centimeters. Reducing the overall triangle size won't help here, similar to front tower refinement. Further, the white tower is far away from the camera, so a very small triangle size might lead to polygons with hardly no image content. In this case, bigger is better. The first thing that might help here is quality. As described earlier, increasing this value forces 3D4 to work longer on the footage. So, increase this parameter drastically so that the procedure has every freedom to work with the footage. Be aware, this will lead to a much lower performance. But for this demo, we choose an extreme setting. Since the image quality is not ideal and 3D camera quality declines a bit due to the object's distance and image quality, the procedure should be a bit more tolerant towards artifacts and slight 3D camera errors. Further, the White Tower doesn't have many flat surfaces. There are setbacks, leaping bricks, everything seems to be crooked and uneven. That's a pretty hard task for refinement, so we need some tolerance for this unevenness as well. This tolerance is set with a lower sensitivity value. Okay, as we learned, a high quality value will have a huge impact on performance. Maybe there's a way to again save time with another option. Have a look again at footage, especially the last frames. Here we see the ground is hardly visible, so these frames won't contribute to a proper refinement of it. And that's exactly how we can again increase performance. Reduce the amount of frames used for refinement. Of course, there are plenty of frames that we can use, but for this demo, we'd like to go a bit extreme and use just the first 3 frames. Here, tower and ground can be seen very good, and we like to save some time, right? Using 3 instead of 17 images will improve performance drastically. But of course, this might influence the refinement quality. But that's why we modified sensitivity and quality. So, back to refine polygons. At parameter use footage, choose from reference cameras within frame range only. By the way, it is also possible to simply select the needed cameras in Object Browser and use them here with option from selected cameras only. Alright, let's start this experiment. Again, this part was sped up to show what happens now. Nice. This looks much better than before. The interpolation at the edge is gone and even details like the setback in the wall could be refined. Even better, this refinement didn't last longer than the other 2. The reduced amount of used cameras really helped having a performance destroyer like parameter quality set to 1. And again, we have a nice low poly model. Of course, there's room for improvement, but for this demo, the result is sufficient. It is highly recommended to always play around with all the parameters refined polygon provides. It's hard to say upfront which setting will be the best, but the high speed of the refinement procedure allows us to do so. Awesome! Just look at the reconstruction. We could create a quite precise 3D model of the castle in just a few simple steps, lasting minutes rather than hours. Nice! So, originally someone told something about a textured 3D model. When scrubbing through the cameras, well, textured looks different. That's the last step in this course, creating a texture and export the 3D model. At first, combine all 3 3D models. Texturing a single model might be a bit more accurate than with multiple ones, since 3DE4 can use the 3D positions of all polygons within the single model and therefore might differentiate objects better within the scene. Select 3D models, merge 3D models, and boom! As also displayed in Object Browser, there's only one 3D model left. Okay, it's texture time. Open menu 3D models, generate UV texture map. In the requester, at first set a path and file name for the image file. Next, define an output resolution. Considering the 5K footage and the big castle, 4K is appropriate. Output format is set accordingly to your needs. 8-bit and 32-bit formats are supported. Auto-tracking masks can be left untouched. There aren't any in this project. All reference cameras should be used as a source image, so set both parameters accordingly. Border around each face defines the minimum distance of each face within the texture map. As we can see here, all polygons are widely placed to get a compact texture map. A higher value prevents annoying artifacts in cases of texture map anti-aliasing, but decreases the individual size of each polygon within the map due to the fixed resolution. So, a correct value highly depends on your needs regarding anti-aliasing. Hit button OK. And after a short while, we have a texture map. In Attributes Editor, parameter texture mapping was set automatically to display the newly created texture. Let's have a look at it. At first here, scrub through all cameras. Yeah, this is nice. Of course, nothing is moving around anymore. The mapping procedure really could differentiate the different point of views and stitch the content from every camera seamlessly together. A final check in lineup. If we turn the 3D model on and off, we see just a slight difference to the original footage. This difference isn't caused by a false reconstruction. The texture map simply has an average brightness of all cameras. So, in most cases, the 3D model's brightness won't match with the footage ones in the individual cameras. Alright, we finished our task of reconstructing the two towers and walls. So, last step here is exporting the model so other departments can enjoy it as well. Select 3D models, export 3D models as OBJ. Here again, set path and file name. Then activate Export Material File. With this file, a different software gets an info file containing definitions of textures for this model. Its UV coordinates will be exported as well with the activated toggle button above. That's it! A great reconstructed castle was delivered. By the way, 3DEforce Maya export script is able to export UV textures as well. So if you'd like to export directly to Maya, choose this script. That was quite a journey, right? We learned about shooting perfect reference frames. Shoot all frames with the same focal length value, do not change focus during shooting, as well as set a low ISO and high aperture. And of course, use a damn tripod. Further, 3DEforce reference frame tracker was introduced. We saw how to track features in reference frames using the semi-automatic and fully automatic approach. In the latter, auto-tracking masks and find badly tracked points were a tremendous help. Last, we used the track points to create a low-poly textured 3D model of the castle with refined polygons and create UV texture map in just some minutes. The speed of this procedure is just incredible. Well, that's it. Thank you very much for watching. I hope you enjoyed this tutorial.